This particular experiment was repeated later in the century using even better equipment with new ideas and new understandings. And I'd like to share with you precisely the exact language of what the scientists at the Weitzman Research Institute discovered when they repeated the double slit experiment. Vacuum implies that this vessel is empty, but we know it's not completely empty because there are still little photons of light that remain in this vessel. So the question now is, where are those photons? The experiment begins with something seemingly very innocent, a glass vessel, a vase, where all of the air has been completely drawn out of this vessel to create what we call a vacuum. So a vacuum implies that this vessel is empty, but we know it's not completely empty because there are still little photons of light that remain in this vessel. Scientists know this. So the question now is, where are those photons? They want to get a baseline and see where the photons are right now. So the first part of this experiment, they draw the air out of the vessel, and then they measure where these photons are in the vessel. Are they all piled up on the bottom? Or are they floating around the inside? Or are they all stuck to the edges? And what they found was no surprise. The vessel showed that these photons are completely random. They're completely random. By the way, these are the same kinds of photons, the particles of matter that make up the atom itself, that we described in the last episode. So we're dealing with these fundamental particles of the stuff that our world is made of, and that's important. So the scientists found that the distribution of the photons in this vessel was completely random. No surprise, that's what they expected. The next piece of this experiment is where, while the experiment is fascinating, what I find really fascinating is the thinking of the scientists that made the experiment possible. For a scientist trained in the scientific method, based upon all of those false assumptions that we saw earlier in this program, those assumptions of separation, for the scientists to move out of that box of thinking and begin asking new questions like, what if our assumptions are wrong? What would that tell us about our world? That's where it gets really interesting, and that's what the next part of this experiment is all about. Because what the scientists did was, into the vessel that had completely random photons, they put human DNA. Human DNA, because they wanted to see if human DNA has an effect on the photons. And before I go any further, I just want to invite you to think about what they're asking. Photons are the stuff this world is made of. DNA is the stuff we're made of. And they're asking, scientists are asking in the laboratory, does the stuff we're made of have an effect on the stuff our world is made of? This is where it starts to sound like science fiction, or at least something that an advanced yogi would be working with. But these are in a bona fide scientific laboratory, these questions, this is where they're being asked. So here's what they did. They took human DNA and they placed it inside the vessel. And then they measured the DNA again to see what would happen. And they measured the photons again to see what would happen. And the results of this experiment changed the way we have been conditioned to think about ourselves and the world. Because the photons went from being completely random when they were first measured, and in the presence of the human DNA, the photons are no longer random, they are ordered. They followed precisely the geometry of the DNA. The DNA was having a direct effect on the photons. The stuff we're made of is having a direct effect on the stuff our world is made of. Just like some of our most ancient and cherished indigenous and spiritual traditions have always told us that we are connected to the world. So this is the first experiment. Human DNA has a measurable effect on the stuff our world is made of. Now, although the observer effect was first documented during the first double-slit experiments early in the 20th century, as happens so often with these very important experiments, this particular experiment was repeated later in the century using even better equipment with new ideas and new understandings. And I'd like to share with you precisely the exact language of what the scientists at the Weizmann Research Institute discovered when they repeated the double-slit experiment. In 1998, scientific headlines all over the world reported this experiment, and they read, and this is a quote, "Researchers at the Weizmann Institute of Science conducted a highly controlled experiment demonstrating how a beam of electrons, so these are quantum particles, a beam of electrons is affected by the act of being observed." But even beyond that observation effect, that was noted early in the century. But listen to this. Listen to the new portion of this discovery. The scientists said, quote, "The experiment revealed that the greater the amount of watching, the greater the observer's influence on what actually takes place," end of quote. And this was actually reported in the very prestigious journal Nature, February 26, 1998, volume 391, if you want to look it up for yourself. This experiment is telling us that not only are we intimately enmeshed with the world around us and with the world within us, but the more focus, the greater our focus, the greater the attention that we give, specifically something that is happening in our lives, the greater the effect. But I think this is interesting because we already knew this if we followed the principles in some of our most ancient, again, and cherished spiritual traditions. For example, in the sutra from the Mahayana Buddhist traditions, there is a statement that essentially summarizes what the Weizmann experience just told us. And that statement says, quote, "Reality exists only where the mind creates a focus." Reality exists only where the mind creates a focus. So the ancient Buddhist traditions, they didn't have the science, but they sure understood the principle. They understood the mechanism. Where we create this convergence of thought, feeling, and emotion, where we create that focus, that is us observing the world around us. And it is that experience and the fact that that experience has such a powerful effect in our lives that actually made Albert Einstein, it was making him crazy. This is the piece of the puzzle that Einstein was never able to solve. He began early in the 20th century with his theories of relativity, and he was always searching for a unified theory, a unified field theory. Here's what I mean by that. In a unified field theory, it's where a scientist like Albert Einstein creates a single story that incorporates all of the facets of nature and physics and mathematics into one coherent story of us, our universe, and our relationship to it. The unified field theory has been an elusive theory. It is yet to be discovered. Einstein and the world supported Einstein, thinking that this is the man. If anyone could do it, he could do it. Here's where Einstein got stuck. And he actually admitted this on his deathbed in the early 1950s. He got stuck because he did not like the idea that we are so intimately connected with our universe that we could have any influence whatsoever on the universe in one place with us being in another place. And as I mentioned earlier, he actually had a name. He called this spooky action at a distance. He called this spooky action at a distance because to him it was spooky. One of the things I find particularly fascinating is that although Einstein was working with the same mathematics and the same equations as his friends and colleagues, he came to the conclusion that we are separate from one another and that we are separate from the universe and that we can be observers in the universe. However, a dear friend and colleague of Albert Einstein's, a man that lived much longer than Einstein and had a tremendously powerful influence in quantum physics at Princeton University in our world today, was Professor John Wheeler. He passed away just a few years ago. So John Wheeler and Albert Einstein, they were friends, they were colleagues, looking at the same equations, the same math, drawing vastly different conclusions. So while Einstein believed that we're separate and have no effect, Wheeler said just the opposite. And I want to share with you John Wheeler's exact words, just so you can hear his process and his thinking and how passionate he was about this. John Wheeler said, "We had this old idea that there is a universe out there somewhere. And here's man, he called the observer, safely protected from the universe by what he called a 6-inch slab of plate glass. Okay, so it's not really plate glass, but that is his way of saying that there is something between us and the universe out there. But he continues. He said, now we learn that to even observe an electron, we have to shatter that plate glass. Listen to what he said. He said, so the old word observer simply has to be crossed off the books. He said, there are no observers. We must put in the new word participator. No observers, only participators. So what does this mean? I'm going to just very, very quickly encapsulate this idea and why it's so powerful in our lives. Because what John Wheeler has just said to us tells us that we will never find the smallest particle of matter, no matter how many atoms and quantum particles that we smash into one another and break into a bajillion pieces looking for smaller and smaller pieces, and we will never find the edge of the universe, no matter how far we look to the edge of the cosmos and how technologically sophisticated our equipment is. And here's the reason why. What John Wheeler just said to us is that every place that we look into the universe, every place that we look